טוב, שלום לכולם ולכולן. אני שמח לפתוח את מושב הצהריים של הכנס השנתי השלישי של המרכז לחקר מגפות באוניברסיטת תל אביב. אני פרופסור אודי זומר מבית הספר למדע המדינה, ממשל ויחסים בינלאומיים, ואני חבר בוועדה המדעית של המרכז. המרכז, מבחינת המחקר שלי, היה מאוד משמעותי גם מבחינה אינטלקטואלית וגם מבחינה מימונית. כמה מהדוקטורנטים שלי קיבלו מלגות שאפשרו להם לעשות מחקרים שבאמת התפרסמו בסופו של דבר בנושאים האלה, על הממשק בין פוליטיקה לבין מגפות, או הפוליטיקה של מגפות. אז אני מאוד שמח להיות חלק מהמיזם הזה, או מהמרכז. אנחנו נשמע היום 4 הרצאות, ואני אציג אותם כל פעם לפני שהם יעלו. אז ההרצאה הראשונה היא של דוקטור אינס צוקר ומספר שותפות ושותפים. אינס היא מבית ספר להנדסה מכנית ומבית ספר פורטר לסביבה מהפקולטה להנדסה, והכותרת היא The Role of Tropospheric Ozone in Controlling the COVID-19 Outbreaks. אז אינס, בבקשה.
Hello everyone. Yes, so thank you for the kind introduction. I'm very happy to be here today. The last session was really interesting to me. I come from a very different field of research, as you will see in the next slide. So thank you for the invitation. In my lab, we study environmental nanotechnology. As I said, very different from what we heard in the previous session. We basically look at nanotechnology in environmental lenses. From the bright side, we use the properties of nanomaterials that are tunable in order to create novel materials for water treatment, for soil treatment, and so on. One example is our development. Let me add just a laser pointer. All right. One example that I give here is our development of multifunctional adsorbent. We take activated carbon and we deposit or grow molybdenum disulfide nanosheets on top of them in order to have multifunctional adsorbents. The activated carbon will absorb organic pollutants as they typically do, but the nanomaterial will absorb heavy metals. We also look at the dark side of things and we say, okay, if these materials are so reactive, then they might have negative effect on the environment. And in that context, we look at engineered nanomaterials, but also we look at incidental nanomaterials like nanoplastics and microplastic, which you probably heard of. And we test, we look at the adsorption of different pollutants on top of the plastics, their joint toxicity, and so on. And then in the last part, we look at advanced oxidation processes, mostly related to ozone treatment in order to degrade organic pollutants. And our last development in the field are nanobubbles that are filled with ozone gas in order to deliver the oxidants in the subsurface where we have contamination. And from that exact starting point, Corona arrived. And then we wanted to get involved and to see if ozone might contribute to the migration of the pandemic. So looking a little bit about the global growth of COVID-19 outbreaks, it's attributed to, of course, severe respiratory syndrome, but it also have significant impact on the health, the economics, and overall well-being. While the person-to-person transmission is the primary pathway, there are secondary pathways such as surface contamination and airborne transmission, and that is the focus of our studies. So what we did is that we looked at, in the first study, at disinfection of surfaces using ozone. And in the second study, we looked at the role of tropospheric ozone in controlling COVID-19 outbreaks. So a little bit about ozone. Ozone is a very strong oxidant, typically used for disinfection, but also, as I said, in our lab, we use it for degradation of organic pollutants, of chemicals that exist in water. We create it in lab, and we do that by electrical discharge of oxygen gas. It breaks and then it reforms as a molecule with 3 oxygen atoms. It has some advantages as a gaseous disinfectant because you can produce it on site. It has no residues, not like chlorine, for example, and it reaches every surface and every void in a treated zone. At least this is the hypothesis, which we will confirm in several slides. And in this bottom image, we see an old study that focuses on the development of ozone treatment for hotel rooms. In relation to SARS-CoV-2, the severe restrictions on the direct use of the virus in laboratory experiments lead us to look, us and other researchers, of course, to look on other coronavirus surrogates. So in this slide, we see the collaboration of our lab together with Moshe Daseo from the Israeli Faculty of Medicine in Bar Ilan University. And we used his pseudoviruses as surrogates for the SARS-CoV-2. What we see in the in the right graph is the normalized infection as a function of exposure time to ozone. 100 ppm of ozone is relatively low exposure. And we see that the different surrogates that are typically being used and the pseudovirus behave very similarly, but not in long time scales. When we expose the different surrogates to ozone in longer time scales, we see a big difference, and control experiments show us that this reduction in infection for the pseudoviruses comes from its sensitivity to dryness. After this 60 minutes of exposure to ozone, all the droplets of the surrogates actually dried, and then in the reconstitution, we kind of lost the pseudoviruses. However, after 30 minutes, it's quite safe to say that the surrogate, the pseudovirus surrogate, will help us to look at ozone disinfection. So this is the system, very simple system that we constructed. We have the ozone generator here, an exposure chamber, and we have an inlet port and ozone analyzer, so we will know the ozone concentration in the chamber. Then we want to look at at the normalized infection, again at 3 different or 4 different ozone concentrations, 30 ppm, 100 ppm, and 1000 ppm, part per million. And we had the V as it's in gas and volume and not in solution. And of course, this is not surprising. We see the effect of ozone concentration when the ozone exposure increases, meaning the CT, the concentration multiplied by the time. When the exposure increases, then the infectivity decreases. So this is not really surprising, and the trend actually follow, or the log inactivation follows previous studies. The next thing that we did is that we looked at an important parameter that affects indoor disinfection, and this is the surface material to be treated, right? Because we took different type of surfaces that are typically used. For example, nickel and copper are very common in electrical devices, brass in jewelry, in decoration, and so on, glass and aluminum alloys, general purpose use, and stainless steel in elevators and so on, kitchenware. What we look at here is the normalized infection. Again, in two different experiments. One is at exposure to 1000 ppm ozone for 5 minutes, and then at 0 ppm ozone for 5 minutes. And we see that indeed the infectivity decreases significantly. And there's also a significant difference between these three, the nickel, copper, and brass, as compared to glass, stainless steel, and the aluminum alloy. Try to understand the mechanism and to correlate these results to different characteristics of these surfaces. So we started with looking at their functional group. We didn't find any explanation there. However, when we looked at the hydrophilicity of these surfaces, we definitely see correlation. Hydrophilicity is being measured using contact angle. We basically put a drop of water on the surface and measure the angle in between the droplet and the surface. And we see that for nickel, copper, and brass, these are all hydrophobic surfaces, whereas glass, stainless steel, and aluminum alloy are more hydrophilic. And therefore, this really explains the difference that we saw there in the blue bars. So when we have higher contact between the droplet and the surface, higher infectivity is being achieved. Last thing that we did in this research, and then we're going to move to the ambient ozone concentrations, we looked at this hypothesis of ozone that can be effectively penetrate to every part of the room. So luckily, this is the one and only experiment that we were able to play with a dollhouse. So we put droplets of the surrogate in different areas on the top surface and bottom surface, interior surface, and so on. And interestingly, or not surprisingly, we saw that the infectivity decreases to very similar rates. So this basically suggests that if we apply ozone properly, it may overcome the low accessibility of many other commonly applied liquid disinfectants, and this enables complete and effective disinfection. All right, so moving to the second part of the talk, the tropospheric ozone. We were very happy to see the results from the previous research, and then we said, okay, ozone is out there always, right? However, in much lower concentrations. The concentrations are typically between 20 to 120 microgram per cubic meter, which are, we talked earlier about ppm or ppb, which are 30 to 170 parts per billion. So very low concentration. However, the exposure time is much higher, right? So we wanted to understand if there's a correlation between ozone concentration and other ambient parameters to the COVID-19 cases. In order to do so, we had two approaches. Maybe I will go back again to the question that we asked. Does stratospheric ozone affect transmission? And if so, how do other parameters like meteorological or environmental parameters affect? So we used the following approaches. One is that we looked at the large-scale statistical analysis for coronavirus infections in Israel and correlated them with local stratospheric ozone concentrations and other relevant factors. And then we also went back to lab and looked at inactivation tests using ozone gas that were conducted in order to investigate the impact of selected conditions on viral survival. So looking at the COVID-19 measures, we looked at accumulated cases, hospitalization, deaths, and in terms of environmental variables, we looked at the temperature, the absolute humidity, relative humidity, particulate matter, ozone, of course, and NOx. So these are, this is basically what's called air pollution. So nitrogen monoxide is known as air pollution from transportation and other human activities. So first, We looked at the different parameters, the different meteorological and environmental parameters over time. And we see that there's a similar trend among the three metropolitans, Be'er Sheva and Tel Aviv and Haifa, and therefore we kind of unified all of these results together in the next slide. Another thing that we can see is that there is a distinct seasonal trend, right? For example, when we looked at, sorry, I can't really see from here. Okay, so when we look at the ozone, for example, we see higher concentration in the summer, low concentration in the winter, and that makes sense because ozone is being generated from reactions of the sunlight with hydrocarbons and nitrogen monoxide. And then we see the same thing with the temperature and relative humidity, but we see opposite trends for the NOxes and the ozone, which also makes sense because ozone is a secondary pollutant that is being created from reaction, from oxidation of these NOxes. So we try to find relationships between environmental parameters and COVID health data. And at the beginning, it didn't really work out for us. We looked at the total accumulated deaths as a function of ozone concentration and NOx concentration. The correlation was very, very weak. However, what we could say is that roughly when the NOx increases, the death increases with it. And when the ozone increases, the death decreases. And these trends are actually opposite for the ones that were measured in different places around the world. For example, in the US and in Italy, they found positive correlation for the number of deaths with ozone levels. And they actually associated that with the ozone effect on respiratory symptoms and respiratory system immunity. What was interesting to me is that the study that was conducted in Italy actually talked about the elevated ozone concentration and found a reasoning for that. They say that in all the cases where ozone concentration was high, it was basically during the COVID-19 shutdown, which makes sense because when there's a shutdown, there's no transportation, there's no air pollution, so there's no NOx, and the ozone concentration increases. So that's starting to be a problem for us. It means that we will not be able to actually correlate between the ozone concentrations and its effect on the disease itself. We also did that with R effective. So this is the number of accumulated cases for a week, and the same accumulated cases for a week, but with the generation period, tקופת האינקובציה. All right, so we look at R effective. When it's above 1, the disease is increasing, and below 1 is the opposite. And here we see better trends, right? We see that when ozone increases, the R effective decreases. So the effect of ozone on COVID-19 transmission was found only here, only in the cold and dry seasons, only in the winter, where low ozone corresponds to high COVID effect. And this time, similar observations were seen in China, and the possible reasoning for that is, of course, ozone may disinfect, and ozone disinfection may dominate in the winter, but also there might be a direct effect of the low humidity because it might increase respiratory infection diseases. So we see that ambient ozone can cause confounding effects on COVID-19 transmission, which are related to ambient temperature and humidity levels, right? But at the same time, it is related to other variables like lockdowns protocols and corresponding pollution levels. So that means that if we want really to isolate the confounding effect of ozone on the virus, we need to go back to lab. And that's exactly what we did. We constructed a new system. This time we used MS2 bacteriophages as surrogates for SARS-CoV-2. It was used in many other studies. We put droplets of the bacteriophages on a glass slide. And what we see here in the figure is basically the controls. We made the glass surfaces hydrophobic by adding saline, and we see that it actually helps to the vitality of the bacteriophages. If we don't have coating, we basically have higher inactivation. We clean the surfaces with ethanol, which was also important. And we see that after 4 hours of exposure, this time, again, the ozone concentration is really low, so we need much longer exposure time, but the droplets, they dried, but the inactivation was not affected. All right, so again, we look at the ozone, the effect of ozone concentration, this time in much lower ozone concentrations and with the MS2 bacteriophages. And again, not surprising, when the ozone concentration decreases, the log inactivation decreases as well. So again, ozone concentration goes up, inactivation goes up. And we kind of approached the environmental concentration of 100 ppb. It's really hard to do that in lab conditions, but at least we have this value now. So continuing with that, we looked at the effect of humidity. And what we see here is that when the humidity goes up, the inactivation goes down. So we try to isolate the effect of the absolute humidity on the virus and on the ozone itself. So viruses exhibit low stability in dry atmosphere. This is known, and ozone is stable in dry atmosphere. So both of these facts actually support the results that we see in the figure. However, when we look at the effect of temperature, we see that when the temperature increases, the inactivation increases. This is different from what we saw in the environment, right? So we try again to isolate the effect. Viruses have lower stability in high temperature, and ozone is less stable in high temperature. So we expect to see lower inactivation, right? These are actually opposite trends. And therefore, we concluded that the effect of temperature on the virus itself dominates the inactivation in presence of ozone. These are the conclusions. It's, I know, a lot of words, but I will walk you through it. So ozone is an effective disinfectant. It can be a powerful tool to minimize viral transmission. Indoor inactivation was demonstrated even in low ozone concentration or low ozone exposures and in hidden surfaces. We see that disinfection occurs on various surfaces, and we saw a positive association with hydrophilicity. We examined the hypotheses which link local increases in concentration of ambient ozone with the spread of the pandemic. But this was really dependent on temperature and absolute humidity. And it happened only in the winter, at least in Israel. There are many coexisting conditions that affect the ozone activity. And we looked at the fact that elevated humidity in lab were shown to inhibit the inactivation efficiency, while higher temperature increases the inactivation rate. And therefore, we see that the correlation between the vitality of the virus and R effective cannot be expressed in environmental scales because of the involvement of many other factors. And basically, that's it. I want just to thank all the collaborators and the TCCP grant and my group and you. Thank you. To stabilize ozone. No, the other way around. Yeah. There are many ways to destabilize ozone in order to create radicals. However, I think that at least in the environmental perspective, when it happens, it has to occur in a humid environment. So it doesn't really work together. But definitely when ozone is being diminished, typically radicals are increasing, hydroxyl radicals. Okay, thank you.